Today we will begin our discussion on the methodology and guidelines for structural design of a practical reinforced concrete frame building, for example, the office building, for which the architectural floor plan of a typical floor is presented in assignment number 1. The practical guidelines that we discuss in the context of the office building, for which the architectural floor plan of a typical floor is presented in assignment number 1, are applicable in general to the structural design process of any reinforced concrete building frame in a frame building structure, as the principles and methodology that we discuss in the context of the structural design process for the real reinforced concrete frame building that is presented in assignment number 1. Well, as a review, the figure in assignment number 1 displays the architectural plan of a typical floor of an 11-story office building that is to be constructed in a densely constructed terrain, for example, the Connaught Place in Delhi, on a flat topography, as a reinforced concrete frame structure, being the primary structural or load resisting mechanism for the building frame or building structure in question. Well, in addition to the reinforced concrete building frame, that is the primary structural system or the load resisting system for the office building in assignment number 1, there are some non-structural or architectural components in the building, for example, the exterior walls in the building, which are 230 mm thick and are constructed in brick masonry, and the partition walls, which are 115 mm thick that is half brick walls provided for purposes of partition of enclosures in the architectural floor plan that is presented in the figure. Displayed in assignment number 1. Floor to floor height is 3.4 meters. Therefore, with those parameters, that is the building site, topography of the building site, terrain characteristics of the building site, seismic location of the building site, and the height of the building with the number of stories, we are required to complete the structural design process for the reinforced concrete building frame, that is the primary structural system or load resisting system of the office building, of which a typical architectural floor plan is provided in the figure of the assignment. Now, as we discussed earlier, the first step in the structural design process of a reinforced concrete framed building structure, for example, the office building considered in assignment number 1, is to devise a structural framing plan or a structural framing scheme of the building. Now, the development of the structural framing plan or the structural framing scheme of a practical building structure that is constructed as a reinforced concrete building frame as the primary structural system is generally performed following some empirical or practical guidelines for conceiving the structural framing plan of real or practical frame building structures, and we will be discussing these empirical guidelines that are based on past experience for the conception of the structural framing plan or framing scheme of reinforced concrete frame building structures in the context of the office building, for which the typical architectural floor plan of a typical floor has been presented in assignment number 1. Now, proceeding to the guidelines, proceeding to the practical or empirical guidelines for developing a structural framing plan of a real reinforced concrete frame building structure that is to be constructed in the field from a given architectural plan of a typical floor of the building, such as the architectural floor plan shown in assignment number 1 in the figure. The conceptualization of a structural framing scheme is an exercise in optimization of structural strength versus economy. That is, the structural framing plan or the structural framing scheme of a practical reinforced concrete frame building structure, for example, the office building, for which the architectural floor plan of a typical floor is shown in figure 1 of the assignment number 1, is based on past experience of structural engineers with designing similar structures in a cost-effective and structurally viable manner, following some empirical or practical thumb rules for achieving economy as well as structural viability. So today we'll discuss these general guidelines that are followed by structural engineers based on past experience with similar structures in order to generate the structural framing plan or the structural framing scheme of the office building presented in assignment number 1, that is to be constructed as a reinforced concrete building frame as the primary structural system of the building from the given architectural plan of a typical floor of the building that is presented in the figure of assignment number 1. Well, the first practical or empirical guideline for developing a structural framing scheme or a structural framing plan for a reinforced concrete frame building structure, for example, the office building in assignment number 1, is that all the full height masonry, that is brick, partition and filler walls with height more than 2 meters should be supported by beams. Otherwise, the floor slabs will become too thick and therefore uneconomical. In this context, it is worthwhile to mention that in a typical reinforced concrete frame building structure, for example, the office building that is to be constructed with a reinforced concrete building frame as the primary structural system in assignment number 1, the economical thickness of a floor slab in a reinforced concrete frame building structure is between 75 mm to 150 mm. The typical floor thickness is 100 to 125 mm, depending on the unsupported span of the floor slab. Well, intuitively, therefore, as we just mentioned, the conception or conceptualization of a structural framing scheme that is cost effective for a practical reinforced concrete frame building structure involves an exercise in optimization of structural strength versus economy, and therefore to minimize the cost or the thickness of the floor slab, the most basic empirical guideline that is followed by structural engineers is to support all full height masonry or brick partition and filler walls with height greater than 2 meters by beams. Well, the second guideline, based on considerations of economy as well as structural viability, requires an understanding of the load transfer path, or the path of load transfer of the gravity loads from the floor slabs to the foundations of the building. And as we have discussed earlier, with reference to the earlier presented slides on the distribution of externally applied gravity loads, that is the vertical dead loads and the live loads acting on the floor slab, the beams transfer the vertical gravity loads acting on the floor slabs to the columns, and the vertical gravity loads acting on the tributary area of the beam in question. For example, beam B1, B2, shown in this figure, with the trapezoidal tributary area shown as the shaded region, is deemed to be transferred or supported by the beam B1, B2. In case of a rectangular floor slab, such as the one shown in this figure. While the vertical gravity load acting on the triangular tributary area is deemed to be transmitted or supported by the beam A1, B1, in case the floor slab is rectangular. Well, the guideline is based on the yield line theory for floor slabs, an advanced concept that is generally taught in postgraduate or graduate level courses, wherein rectangular slabs generally exhibit yield lines under the action of vertical gravity loads at the yield limit state that are trapezoidal along the longer direction of the floor slab and triangular along the shorter direction of the floor slab. So based on the semi-empirical concept of the yield line theory as well as the empirical data obtained from experimental testing of rectangular floor slabs subjected to vertical gravity loads, the load resisting mechanism of a floor slab is assumed to be depicted by this figure in case of vertical gravity loads, wherein the vertical gravity loads acting on the tributary area that is trapezoidal in shape and depicted by the shaded region which is a trapezium is supported or resisted by the beam B1, B2, while the vertical gravity load acting on the triangular tributary area is transmitted or resisted by the beam A1, B1. Now with that intuitive understanding of the path of load transfer for the vertical gravity loads from the floors or the floor slabs to the beams, one can visualize the practical or the empirical guideline that should be followed for locating the columns, since the beams in general are located to ensure that the full height partition or filler walls are supported by the beams so that the floor slabs do not become too thick or uneconomical. Well, in order to achieve the maximum economy for the beams in a reinforced concrete building frame, therefore, the columns, for example, B1, column B1 shown in this figure and column B2 shown in this figure, should not be spaced too far apart. Otherwise, the beam will become or will have to be too deep and therefore uneconomical. For example, considering a 100 thick floor slab, a typical value for thickness of the floor slab in a reinforced concrete building frame, assuming the self weight of reinforced concrete as 25 kilonewton per meter, the uniformly distributed load due to the dead weight or the self weight of the floor slab is 2.5 kilonewton per meter. As a result, the equivalent uniformly distributed load that is deemed to be transmitted from the trapezoidal tributary area of the beam B1, B2 to the beam B1, B2, shown as the shaded region. Or the shaded trapezium, with the area R is calculated as the uniformly distributed load with the uniform intensity of 2.5 kilonewton per meter square times the area of the trapezoidal tributary area for the beam B1, B2 divided by the length of the beam in kilonewton per meter units. So with that simple calculation of the equivalent uniformly distributed load with the uniform intensity acting on the beam B1, B2, one can intuitively visualize that longer the span of the beam B1, B2, deeper or larger will be the depth of the beam B1, B2. Therefore, less economical or more uneconomical will be the beam B1, B2. Therefore, based on the engineering intuition just discussed for the economy of the beams, for example, beam B1, B2, the spacing of the columns should not be too large. For example, in case of beam B1, B2, the spacing of the columns B1 and B2 should be within the economical range to ensure that the beam B1, B2 does not become uneconomical. And as a thumb rule, based on past experience of structural engineers with RC or reinforced concrete building frames, the economical spacing of columns to ensure that the beams do not become too deep, or the depth of the beams does not become too large and therefore uneconomical, is limited to 9 to 10 meters. Limiting value may be considered as 9 meters for the maximum economical spacing of columns. Otherwise, the beams will become too deep and therefore uneconomical. On the other hand, there is a lower limit to the economical spacing of the columns, while the upper limit, based on empirical guidelines on the economical spacing of the columns, is 9 to 10 meters, with the limiting value as 9 meters adopted in this study. The minimum limiting value of the economical span of the columns is 3 meters as observed in practice with similar reinforced concrete building frames. The rationale of the lower limiting value of 3 meters for the economical spacing of the columns is that the column spacing that is too low, for example, column spacing less than 3 meters, will result in too many columns. And each column involves cost or expenditure, since columns are reinforced concrete elements. Each and every column adds to the cost of the reinforced concrete building frame, and therefore spacing of the columns that is less than the lower limiting value for economy, that is 3 meters in general, will result in too many columns and therefore increase in cost that is assigned or associated with constructing every column. To conclude, therefore, the discussion on this slide, the empirical or practical guidelines for developing a structural framing plan or structural framing scheme for a real reinforced concrete frame building structure. For example, the reinforced concrete building frame envisaged for the office building, for which the architectural plan of a typical floor is presented in assignment number 1, may be summarized as follows. All full height masonry, brick or partition and filler walls with heights greater than 2 meters should be supported by beams. Otherwise, the floor slabs will become too thick and uneconomical, and columns should be located in the economical range of spacing, that is, the economical spacing of columns should range between 3 meters, below which there will be too many columns and thus an increase in cost due to the cost of construction that is associated with each column, while the higher or upper limiting value of the economical spacing of columns is 9 meters, beyond which the beams will have to be provided with too large a depth, thus resulting in uneconomical beams. We will now proceed to the more finer rules or finer guidelines based on past experience with reinforced concrete building frames for optimizing the structural resistance versus economy. So, as we were discussing, the development of a structural framing plan for a practical reinforced concrete frame building structure is an exercise in optimizing economy versus structural strength or structural resistance of the building, and the exercise of generating a structural framing plan or structural framing scheme from a given architectural plan of a typical floor of a reinforced concrete frame building structure. For example, the architectural floor plan that is presented in the figure in assignment number 1 that depicts the architectural layout of the various architectural, aesthetic and functional features of a typical floor in an office building in plan view. Now, with reference to our discussion earlier on the previous slide, the development of the structural framing plan or structural framing scheme for a practical reinforced concrete frame building structure from a given architectural floor plan, such as the one presented in figure 1 of assignment number 1, is based on some practical or empirical guidelines that are themselves evolved on the basis of engineering intuition or engineering judgment gained by structural engineers from past experience or past practice with similar building structures. And since these practical or general guidelines for the generation of a structural framing plan or structural framing scheme from a given architectural floor plan, such as the one shown in this figure, which is the same figure that is displayed in assignment number 1. The engineering intuition or engineering judgment that is the basis for the development of the structural framing plan has evolved on the basis of past experience or past practice of structural engineers designing similar building structures, and therefore the term or the prefix empirical, since the guidelines are based on past experience or past practice with similar building structures, the guidelines have been termed as empirical guidelines in this discussion. So, applying those empirical guidelines that are largely based on engineering intuition or engineering judgment gained by structural engineers from past experience or past practice with similar building structures, the first two empirical or practical guidelines that we discussed in the previous slide, that is the practical guidelines for defining the layout of the beams and the practical or empirical guideline for locating the columns lead us to a layout of the beams such as the one shown in this figure. Well, as the first empirical guideline suggests, or recommends, that all full height masonry or brick partition walls should be supported by beams and the definition of full height partition or exterior wall is a wall that is more than 2 meters or 7 feet in height. So, at the outset, the immediate visualization of the beam layout in the structural framing scheme is to provide a beam all along the periphery or the outer boundary, the outer periphery of the floor at each floor, since we are considering a typical floor plan here, and exterior walls that are 230 mm thick and constructed of brick masonry units have been provided along the periphery of the building as mentioned in the question statement of the assignment. So therefore, the immediate action in generating the structural framing plan of the building is to first and foremost provide beams all along the periphery of the building at each floor. And since the interior partition walls that are 115 mm thick and also constructed in brick masonry are also full height walls, the next step in the development of the structural framing plan or the beam layout is to provide a beam under each of these full height partition walls. So, as depicted in this figure, the thick blue lines shown only on the left half of the figure, since the figure is symmetrical about the center line of the floor or the floor plan. Only the beam layouts on the left half have been shown. It is apparent that the beam layout on the right half will be the same as the beam layout on the left half of the center line CL due to symmetry. So the thick blue lines that have been drawn in blue ink along the periphery or the outer boundary of the building or the floor plan represents the beams that support the exterior walls, which are 230 mm thick, while the thin blue lines that have been drawn in blue ink in this typical architectural floor plan, same as the one provided in figure 1 of assignment number 1, represent the beams that support the interior partition walls that are also constructed in brick masonry but are 115 mm thick. So, based on the first practical or empirical guideline that we discussed in the previous slide, the beam layout, the layout of the beams as part of the structural framing scheme or structural framing plan can be completed as shown or depicted by the blue, thick blue or the thin blue lines on this architectural floor plan. Well, the next step then in the development of the structural framing plan is to locate the columns. That is, after locating the beams in the structural framing scheme, we locate the columns, and the columns are located on the basis of the second practical or empirical guideline that we discussed in the previous slide, also based largely on past experience or practice of structural engineers with similar building structures. Essentially, based on engineering intuition or engineering judgment gained from past experience with similar building structures in practice, the second empirical or practical guideline recommends that the columns should be located such that the spacing of between any two adjacent columns ranges between 3 to 9 meters, or at the most 10 meters, which is the economical range of spacing of columns based on past experience or past practice of structural engineers with similar building structures. So, with that guideline or the recommendation in mind, intuitively we locate the columns at a spacing that lies within the economical range of column spacing that is recommended by the empirical guideline, which is 3 to 9 meters or at the most 10 meters, as discussed earlier. Well, there are some additional practical considerations that govern or influence the location of the columns other than the practical or empirical guideline on the economical range of column spacing. And these practical considerations are based on both functional as well as structural factors. For example, columns should be located at the intersection of the beams. For obvious practical reasons or intuitive reasoning, the columns should be located at the intersection of the beams. And so therefore, with those parameters in mind, that is the empirical guideline on the economical spacing or the range of economical range of spacing between adjacent columns, which should be in the range of 3 to 9 meters, and the practical consideration that the columns should be located at the intersection of beams so as to facilitate the transfer of externally applied vertical gravity loads from the beams to the columns. A structurally viable column layout that should also be economical is displayed in this second figure on the slide, wherein, as you can notice, the columns are located at the intersection of the beams, and the column spacing between any two adjacent columns lies in the economical range for spacing of columns based on the second empirical guideline. In addition, there are some structural considerations that need to be accounted in the layout of the columns. Well, if you observe, there are two options for the layout of the columns or location of the columns. Column locations may be defined either by locating the columns at a spacing of 3 meters as exhibited by column A3 and A4 and A4 and A5, which are mutually spaced or which are mutually at a spacing of 3 meters. Alternatively, another layout for the columns or column locations can also be defined while following the second empirical guideline for the economical range of column spacing, is that columns are spaced or located at a spacing of 6 meters. For example, column A1 and column A3 that are located at a spacing of 6 meters, thus omitting a possible column at A2. Now here, in this present discussion, I have used or referred to the location of the columns with some alphabets and numbers. For example, column A1, column A3, column A4 and column A5, and similarly column E1, column E2, column E3, column E4 and column E5. Now, the nomenclature that has been used in the present discussion for identifying the various columns is based on the common or standard practice of defining the grid lines in an architectural plan or a structural framing plan resulting from the architectural plan. And the grid lines, as shown in this architectural floor plan that is in the process of being transformed into a structural framing plan, are generally named or denoted as grid lines AA, BB, CC, DD, and EE as in case of this envisaged structural framing plan. In the X direction, that is one of the orthogonal horizontal directions, and typically the grid lines in the other horizontal orthogonal direction, for example the Y direction, are termed as grid lines 1, 1, 2, 2, 3, 3, 4, 4, 5, 5 on the left of the center line, and 6, 6, 7, 7, 8, 8, and so on the right hand side of the center line of the structural framing plan, that is symmetrical about the center line. So, using the standard practice of defining the grid lines and identifying the columns based on the alphabets and the numerals used in the grid lines, as we were discussing earlier, there are two options that both satisfy or conform to the second empirical guideline. Well, both the first and second empirical guideline for locating the columns. In option number 1, a structural engineer can locate the columns at a spacing of 3 meters, as in case of columns E3 and E4, or columns E4 and E5 that are located at a mutual spacing of 3 meters between any two adjacent columns. Similarly, column A3 and A4 and A5 that are also located at a mutual spacing of 3 meters between any two adjacent columns, or alternatively in the second option, which also conforms to the second empirical guideline for economical range of column spacings, that is 3 to 9 meters, is to locate the columns at a spacing of say 6 meters based on the given architectural floor plan. For example, columns E1 and E3 are 6 meters apart, and there is no column at the grid location E2, and even though the column at E2 has been omitted, although E2 is an intersection of the beams, point E2 lies at the intersection of two beams. There is no column provided at the location E2. The spacing adopted, of 6 meters adopted between the adjacent columns E1 and E3, or for that matter A1 and A3, lies in the economical range of spacing between adjacent columns as recommended by the empirical guideline number 2. Well, since both the options are structurally viable and also economical, one may weigh the two alternatives from the point of view of the functional requirements of the building, which we will discuss shortly, as there are some functional as well as aesthetic requirements that largely are in the domain of the architecture or the architects. Since architects or architecture is more involved with the functional or aesthetic requirements of the building. Therefore, in addition to the practical or empirical guidelines based on optimization of economy versus structural strength for the development of an economical as well as structurally viable framing scheme or framing plan for a reinforced concrete building structure, there are some architectural considerations that are largely based on functional or aesthetic factors, which are more of relevance or concern to the architects, however, have to be accommodated for the overall acceptance of the building plan from both the functional as well as structural point of view. For example, one of the functional considerations that need to be taken into account while locating the columns represented by the rectangles, for example, column A1 represented by this rectangle and column A3 represented by the rectangle here. Similarly, column A4 or E4 represented by the two rectangles respectively. Is that the column should not interfere with the function or use or the occupancy of any particular enclosure that is envisioned in the architectural plan. For example, for purposes of discussion, the functional consideration may be illustrated by considering this conference room right here. Okay. See, as you can see, the enclosure that is demarcated by these four blue lines is a conference room by function. And in order to ensure that the structural framing scheme or the column layout does not interfere with the function of this enclosure or the conference room. Column cannot be located in the middle of this enclosure and has to be located at the outer periphery of the enclosure as shown or as depicted by column C3. In other words, locating a column in the middle of such an enclosure as a conference room or committee room or lecture hall is not acceptable from the point of view of the function, the intended use or the occupancy of the enclosure as a column located in the middle of a lecture hall or conference room or a committee room will interfere with the line of sight of the audience, and therefore functional consideration or the functional requirement of the enclosure dictates that columns should not be located in the middle of the enclosure if the enclosure is a committee room or a conference room or a lecture hall, for example, or an auditorium. Another architectural consideration that needs to be accounted in the column layout, that is in the exercise of locating the columns as part of the development of the structural framing scheme, is that columns should be concealed as far as possible and should be located such that they offer the maximum usable space in the enclosure. For example, considering this office cabin right here, that is circumscribed by this 4 blue lines and named as the office as a cabin. The column E3 is shown at the most favorable location from both the architectural and structural point of view, since the column E3 and for that matter column A3 at the periphery of this office, circumscribed by these 4 lines, are both located such that they can be concealed in the exterior walls highlighted by the thick blue line and the interior walls highlighted by the thin blue line, and therefore will be out of sight, as they will be concealed as far as possible depending on the dimensions of the column or the sectional dimensions of column E3 or column A3 that are required from the point of view of structural resistance of the building. Further, the column as shown in this feasible, structurally feasible and economical framing scheme, that is column E3 or column A3, does not intrude into the usable space of the enclosure. For example, the cabin in case of column E3 and the office in case of column A3, thus offering the maximum possible usable space for the enclosure that is envisaged by the architectural planning. So, based on the considerations of structural strength, economy, as well as architectural requirements, also including aesthetic considerations, for example, concealing the column in the walls as far as possible, the layout of the columns may be finalized, or the columns may be located, keeping in mind all the structural, economical, architectural, and functional, as well as aesthetic considerations that we have discussed in the present slide. Well, we still haven't addressed the question of the spacing between the columns, since it appears that mutual spacing of 6 meters is also acceptable for the given architectural floor plan, and a mutual spacing of 3 meters between adjacent columns is also acceptable for the structural framing plan based on the given architectural floor plan, since both the spacings, that is 6 meters between columns A1 and A3, for example, or columns E1 and E3, for example, and mutual spacing of 3 meters between columns E4 and E5, for example, or A4 and A5, for example, are acceptable from the architectural structural considerations optimized with respect to the economy or economical considerations, as well as the functional, architectural, and aesthetic factors result in a structural framing scheme such as the one shown in this figure, the second figure in the present slide, that illustrates an economical and structurally viable structural framing plan or framing scheme for the given architectural floor plan presented in the figure in assignment number 1, keeping in mind the functional requirements that are presented by the architectural floor plan, as well as the aesthetic considerations that one may consider while arriving at an optimal structural framing plan or structural framing scheme for practical reinforced concrete frame building structure, for which the architectural floor plan is presented in the figure of assignment number 1. Well, converging to the question of the spacing between the adjacent columns, that is the mutual spacing between adjacent columns of 6 meters, for example, columns A1 and A3, or columns E1 and E3 as shown in this figure, or a mutual spacing of 3 meters shown between columns E4 and E5, or columns A4 and A5. Since both the mutual spacings of 3 meters and 6 meters between adjacent columns lie within the economical range of spacing between columns as recommended by the empirical guideline or practical guideline for column spacing, one needs to decide which is the best and the most favorable spacing between the columns, that is 6 meters as shown between columns A1 and A3 in the architectural floor plan, or 3 meters as shown between columns A4 and A5 in the architectural floor plan presented in the figure of assignment number 1. Well, there are some cost and benefit implications of either of the two options, that is, spacing of 6 meters between adjacent columns as exhibited by columns A1 and A3, or mutual spacing of 3 meters as exhibited by columns A4 and A5. And the economical implication of the two options are intuitively based on engineering judgment. Larger the column spacing, provided column spacing is in the economical range of spacing of columns between adjacent columns, lesser will be the cross-sectional area and therefore the volume let me correct that statement. Larger the spacing between the adjacent columns, for example, column A1 and A3, that is 6 meters, greater will be the cross-sectional area as well as the volume or the cost of the individual columns. On the other hand, smaller the spacing between the adjacent columns, for example, columns A4 and A5 with the mutual spacing of 3 meters as shown in this structural framing plan in development. Lesser will be the area, cross-sectional area, and therefore the volume, and therefore the cost of the materials involved in the construction of these columns. In general, the column spacing or spacing between columns within the economical range of column spacing, that is 3 to 9 meters, is selected based on the use or occupancy of the structure. For example, in case of building structures that require large column free spaces, or large column free areas from the point of view of the function or the use of the building structure. For example, commercial buildings such as malls or office buildings, a spacing of 6 meters may be adopted between the adjacent columns, since the spacing of 6 meters lies in the economical range of column spacing for economical design of the beams as discussed earlier. On the other hand, in case of residential buildings, wherein the enclosures are generally 3 meters or 4 meters in dimension. For example, the hostel buildings. In your hostels, the rooms or the enclosures are generally 3 meters by 3 meters in dimension. And economical column spacing of 3 meters, for example, the columns E4 and E5 or A4 and E5 may be adopted since the column spacing between adjacent columns adopted as 3 meters does not interfere with the function or use of the building, and also lies in the economical range of spacing between adjacent columns, that is 3 to 9 meters. In this case, however, adopting the lower limit of economical range of spacing for columns, that is 3 meters, will result in lesser or lower cross-sectional dimensions for the individual columns, and therefore lesser volume and weight, and therefore cost of the material, that is reinforced concrete, required for the construction of the individual columns. So one has to weigh the two options from the point of view of structural viability, optimized versus economy, considering the functional requirements presented by the architectural floor plan of the building. As we discussed earlier, there are some finer additional architectural and structural considerations, including functional requirements that need to be accounted while devising the structural framing plan of a reinforced concrete framed building structure from a given architectural floor plan of a typical floor, such as the one presented in the figure of assignment number 1. Well, in order to understand the aesthetic or architectural requirements, one needs to be informed that a full brick wall, for example, the exterior walls of the office building as presented in assignment number 1, consists of 2 bricks with a total thickness of 230 mm and a length of 230 mm each. So full brick wall as shown, as displayed in cross section, will have a width of 230 mm or 9 inches, with each brick masonry unit constructed with fired clay red bricks having a length of 9 inches or 230 mm. Therefore, in order to address the aesthetic consideration or requirement of concealing the columns within the brick masonry pillar or partition walls or exterior walls, the minimum or the suggested column thickness that is generally preferred by architects is 230 mm, so that the full brick wall is concealed completely within the, or rather, the full brick wall completely conceals the column in case the column has a width of 230 mm. However, with the new seismic design code that is being enforced by Indian standard codes of design practice. The minimum thickness of or the minimum width of columns is 300 meters. But even though the minimum width of the columns that is specified by the new Indian seismic design code is 300 mm, for spans ranging above 5 meters. Most part of the column, that is 230 mm out of the 300 mm width of the column, can be concealed within the full brick masonry wall, and therefore an implicit consideration that is followed in locating the columns is that columns which may have a width equal to the full width of the full brick wall, that is 230 mm, or slightly larger width, are concealed in the full brick walls that are provided as partition or filler walls or the exterior walls of the building. In addition to the architectural, aesthetic and functional considerations that we just discussed, one may mention that the architectural floor plan that is presented in figure of the assignment number 1 depicts an office building, and therefore columns on grid lines 4, 4 and 7, 7 may be omitted as they are not required from the point of view of the empirical guidelines for optimizing economy versus structural strength, since omitting columns on grid lines 4, 4 and 7, 7 will result in a mutual column spacing between adjacent columns equal to 6 meters, that lies well within the economical range of spacing of columns. Additionally, there are some finer points based on engineering intuition and engineering judgment, largely that is gained from past experience or practice with similar structures, as underlined earlier. In order to maximize the structural resistance or the structural strength as well as stiffness of the building, it is intuitive that the columns that are generally provided with rectangular cross sections, such as the one shown here, with a width of 300 mm, B equal to 300 mm, and overall depth of say 900 mm, adopted as preliminary dimensions for any column for the building height stated in the question of the assignment. Should be aligned with their stronger direction, that is the minor axis of the column, aligned along the weaker direction of the building. The additional guideline is purely intuitive and based on engineering judgment, since aligning the columns that with rectangular cross sections such that their stronger direction or the minor axis is aligned along the weaker direction, that is the smaller dimension of the building, will result in greater structural stiffness and strength of the building in the weaker direction, that is the Y direction. In other words, columns which are generally provided with the rectangular cross section should be aligned such that their stronger direction, that is along the depth of the column, is aligned along the weaker direction of the building. that is the smaller dimension of the building, which is along the y direction, as shown in the structural framing plan devised based on the practical or empirical guidelines that have evolved from past experience or practice with similar reinforced concrete frame building structures. From the point of view of optimizing the structural strength and stiffness versus the economy, and also accounting for the functional and architectural requirements including aesthetics. That are envisioned in the architectural floor plan of a typical floor of the building, such as the one shown in figure of the assignment number 1. It is worthwhile to note here that the structural framing plan or structural framing scheme developed as depicted in this figure with either option, that is column spacing of 6 meters between the adjacent columns, or column spacing of 3 meters between the adjacent columns, is acceptable from the considerations of structural strength, structural stiffness, architectural requirements, functional requirements, as well as aesthetics as discussed in detail. One may add that most commercial, residential, or institutional buildings generally have elevators or lifts, and so therefore RC or reinforced concrete shear walls are provided as the core walls for installing the lifts or the elevators. In such cases, the RC shear wall or the core wall, which is a solid RC core wall, that is represented by the double lines in black, is generally idealized or modeled as a solid column with equivalent geometric properties or representative geometric properties in the two horizontal or orthogonal directions x and y. Therefore, the structural framing scheme or the structural framing plan devised based on the empirical or practical guidelines for optimizing structural strength versus economy, accounting for the architectural or functional requirements that are presented by the architectural floor plan of the building. For example, the architectural floor plan presented in figure 1 of assignment number 1, as well as aesthetics. One may select an architectural structural framing scheme or structural framing plan with column spacing of 6 meters between the adjacent columns as shown here. In both X and Y direction. For example, column spacing of 6 meters between columns E1 and E3 in the X direction, or columns A1 and A3 in the X direction, and column spacing of approximately 7 meters between columns A1 and C1 in the Y direction, or A3 and C3 again in the Y direction, and column spacing of between columns E1 and C1 in the Y direction, that is 6 meters, and column spacing of 6 meters between columns C1 and C3 in the x direction, all of which lie within the economical range of spacing of columns. Well, so with that empirical or practical information and background on the development of the structural framing plan or structural framing scheme for the office building, for which the architectural floor plan of a typical floor is shown in the figure of the assignment number 1, using the practical or empirical guidelines that are based on engineering intuition or engineering judgment largely, that are gained from past experience or practice with similar building structures. One can devise the structural framing plan or structural framing scheme for the office building in assignment number 1 based on the architectural floor plan of a typical floor of the office building provided in the figure of assignment number 1. Since the practical guidelines or the empirical guidelines are based on the optimization of the structural considerations with the economical factors as well as architectural requirements and functional and aesthetic considerations that need to be accounted in generating economical and a structurally viable structural framing plan or structural framing scheme. The structural framing plan that is proposed in the previous slide should be acceptable for proceeding with the structural design process for the practical reinforced concrete frame building structure that is serving as an office building and for which the architectural floor plan of a typical floor is presented in assignment number 1. So, proceeding with the step-by-step methodology for completing the structural design process of a practical reinforced concrete frame building structure, the second step after the development of an economical and structurally viable as well as architecturally and functionally satisfactory structural framing plan is to identify the equivalent two-dimensional plane frames or 2D planar frames for the purposes of structural analysis in 2 dimensions for sake of simplicity. As we discussed earlier, the idealized 3 dimensional frame model, or the space frame model as it is more popularly referred to, can be discretized into a series of equivalent 2 dimensional or idealized plane frame models. For example, the plane frame models corresponding to the 2 dimensional planar frames AA shown in the structural framing plan along the grid line AA, spanning in the X direction, that is one of the orthogonal horizontal directions, and in the other horizontal orthogonal direction, that is the Y direction, we can identify and select a similar equivalent 2 dimensional planar frame or 2D plane frame model corresponding to the plane frame 1-1 in the plane of the grid line 1-1, that is the plane frame model or the equivalent 2 dimensional frame model corresponding to the plane frame in the vertical plane of the grid line 1-1, that is spanning in the Y direction. So selecting an equivalent 2 dimensional plane frame in each of the 2 horizontal orthogonal directions, that is the X direction and the Y direction, for purposes of discussion and illustration of the structural design process, we will be referring to the idealized or equivalent plane frame models AA in the XZ plane spanning in the X direction, and the equivalent 2 dimensional plane frame model or the idealized plane frame model 1-1 in the YZ plane spanning in the Y direction. Therefore, proceeding to the next step, that is, after identifying and selecting an equivalent 2 dimensional plane frame model or plane frames in each of the 2 horizontal orthogonal directions X and Y, for example, plane frame model AA spanning in the X direction and plane frame model 1-1 spanning in the Y direction, we proceed to the next step, wherein the structural analysis of the equivalent or idealized 2 dimensional plane frame models is performed for the purposes of determining the unknown internal actions For example, the bending moments M, the shear forces V, and the axial forces P in the individual frame elements. And as we discussed in one of the previous lectures, since the simplified two-dimensional structural analysis of the idealized or equivalent two-dimensional frame models or idealized plane frame models also require the knowledge of the dead load due to the self-weight of the frame and the frame elements. The structural analysis and design is a trial and error procedure, since the dimensions and the cross-sectional properties of the individual frame elements of the equivalent or idealized plane frame models are not known to begin with. That is, the dimensions and the cross-sectional properties of the individual frame elements in the idealized plane frame models AA and 1, for example, are not known or are unknown a priori. The structural analysis follows a trial and error procedure wherein a preliminary design is adopted to begin the trial and error procedure. One may refer to this preliminary design as a trial design, wherein preliminary dimensions of the frame elements, for example, the beams and the columns, may be selected based on past experience with similar building structures. Having selected the preliminary dimensions for the individual frame elements, for example, the columns and the beams, in the idealized 2D or plane frame models AA and 1, for example, we can calculate the dead loads based on the self-weights calculated or computed considering the adopted or selected preliminary dimensions of the frame elements. Having calculated the dead loads based on the self-weight of the trial design, that is based on the selected preliminary design or selected preliminary dimensions and cross-sectional properties of the individual frame elements, one can compute the design loads, particularly the dead loads have been assumed based on the selected preliminary dimensions of the individual frame elements For example, the beam elements and the column elements of the plane frame models. In addition, one can calculate the other design loads, that is, the design live loads for the given use or occupancy of the building by referring to the relevant Indian Standard Code of Design Practice for calculating the design loads or the imposed loads IS 875 Part 2, the 2015 revision. Additionally, the horizontal or lateral environmental loads such as the earthquake loads that are primarily predominant in the horizontal direction, as well as the wind loads, which are also primarily dominant in the horizontal direction, can be calculated by referring to the respective Indian Standard Codes of Design Practice for earthquake resistant design of building structures, IS 1893 2016 revision for calculating the earthquake loads, and the Indian Standard Code of Design Practice for calculating the wind loads, IS 875 Part 3 2015 revision, thus resulting in the various design loads that need to be considered for the structural analysis of the idealized 2D planar frame models or the equivalent plane frame models. For example, the plane frame models AA spanning in the X direction and the plane frame model 11 spanning in the Y direction. Note that the structural analysis is also performed in 2 dimensions, since the plane frame models are considered, or idealized planar frame models are also 2-dimensional. The structural analysis is a 2-dimensional structural analysis and therefore simplified analysis in 2 dimensions. So then, performing the simplified structural analysis in 2 dimensions, or the 2-dimensional structural analysis of the selected idealized plane frame models AA and 11 selected for the purposes of discussion and illustration of the structural design process, one can calculate the unknown internal actions, for example, the bending moments M, the shear forces V, and the axial forces P in the individual frame elements, for example, the beam elements and the column elements, okay? And in the next task, the structural engineer, in the trial and error structural analysis procedure, checks that the design bending moments, design shear forces, and design axial forces, that is, the design values of the internal actions, are within the corresponding limiting values or ultimate values specified by the relevant Indian standard codes of design practice for each of the individual frame elements. If the check is satisfactory, that is, in case the design bending moments, shear forces, and axial forces in the individual frame elements are within the limiting values of the corresponding internal action, that is, the design bending moments, design shear forces, and design axial forces in each of the individual frame elements are within the corresponding ultimate values, then the structural design or the preliminary structural design that is adopted for the trial and error procedure is found to be safe, and no further iterations are required, or no further trials are required to arrive at a structurally viable design. On the other hand, in case the check is not satisfactory, that is, the design bending moments and the design shear forces and the design axial forces computed from the simplified two-dimensional structural analysis of the plane frame models exceed the corresponding limiting values for the respective internal action, then the trial design, the preliminary design that has been adopted for the iterative trial and error structural analysis and design procedure is unsatisfactory, unsafe, in which case the preliminary design will have to be revised and the iterative trial and error structural analysis and design procedure will have to be repeated considering the revised preliminary design or the revised preliminary dimensions. It is intuitive that the preliminary dimensions will have to be enhanced or increased in the revised preliminary design for the next iteration or the next trial to achieve the cross-sectional properties and dimensions for the individual frame elements that result in acceptable values of the design bending moments, shear forces, and axial forces, which are within the corresponding ultimate values for the respective internal action. Therefore, revising the preliminary dimensions, particularly for the frame elements which have been found to be unsafe in the check or the design check, in general, enhancing or enlarging the preliminary dimensions or the cross-sectional properties, the trial and error procedure is repeated with the revised design or the revised preliminary dimensions and cross-sectional properties to perform the next iteration in the trial and error structural analysis and design procedure as shown by this flowchart. The iterative trial and error structural analysis and design procedure for the equivalent two-dimensional plane frames or idealized plane frame models is depicted by this cyclic flowchart, wherein the final design is achieved, or the final design is reached, that is a safe structural design is achieved in the iterative trial and error structural analysis and design procedure once the design bending moments and design shear forces and the design axial forces for each and every individual frame element in the plane frame models are found to be within the corresponding ultimate values for the respective internal action, and therefore acceptable, thus resulting in an acceptable structural design from the point of view of structural strength, as represented by this exit arrow. Now, intuitively, the number of trials that will be required for achieving or arriving at this, the final structural design that is acceptable from the point of view of structural strength and safety, will be less if the preliminary design that is adopted, that is, the preliminary dimensions and cross-sectional properties that are adopted for the individual frame elements in the plane frame models, are as realistic and accurate as possible. In other words, the more realistic and accurate the preliminary dimensions and the cross-sectional properties that are assumed for the trial and error structural analysis and design procedure, fewer will be the number of trials that will be required, fewer will be the number of iterations that will be required in the iterative trial and error procedure, since the initial trial design or preliminary design is quite realistic. Therefore, it is intuitive that for a more efficient and rational iterative trial and error procedure for structural analysis and design, it is desirable to adopt as realistic and as accurate a preliminary design as the trial design for the iterations or the iterative trial and error procedure. Now, realistic and accurate estimates of a preliminary design or realistic estimates of the preliminary dimensions and cross-sectional properties that will result in an acceptable structural design from the point of view of structural strength and safety generally are achieved from practice or experience of the structural engineer with similar building structures in selecting the most rational and accurate preliminary dimensions and cross-sectional properties for the preliminary design. Now, based on past experience or practice with similar building structures, for example, this office building that is 11-story high is located in seismic zone 4 with the column-free spans or column spacing of ranging between 3 to 6 meters. A realistic estimate of the preliminary dimensions for the column section would be 800 by 800, 300 by 800 mm. That is the longer dimension, which is 800 mm, aligned along the shorter dimension of the building as discussed earlier, while the shorter dimension of the column, that is 300 mm, aligned along the longer dimension of the building or the stronger direction of the building, whereas the longer dimension of 800 mm of the column is aligned along the weaker direction or the shorter dimension of the building. Similarly, realistic and rational values for preliminary dimensions of the beam sections may be adopted again based on past experience and practice with the iterative structural analysis and design procedure for similar building structures. The preliminary dimensions of the primary beams may be selected as 230 into 600 mm, whereas Preliminary dimensions for the secondary beams will be selected as 230 by 500 mm for the purposes of adopting a preliminary design, for performing the iterative trial and error structural analysis and design procedure. In order to complete the iterative trial and error procedure and achieve the final acceptable structural design in as few iterations as possible. Sometimes even a single iteration may be sufficient to provide a structurally safe and viable design in the first iteration itself. Only if the estimate of the preliminary dimensions and cross-sectional properties that is adopted in the preliminary design is as realistic and accurate as the final structural design that is acceptable from the point of view of structural strength and safety. Well, there are some minor architectural details that may be mentioned. For example, non-structural components such as the flooring, the roofing, the finishing, and the walling materials may be selected based on the specifications or the finishing specifications of the building. Depending on the specifications, the flooring may be selected as terrazzo paving or vitrified tiles or marble flooring. Marble flooring is generally selected for luxury specifications or very high-end specifications, and thus costly. Thus resulting in a higher cost of the flooring. Similarly, based on the specification that are selected for the finishing, one may use plastic emulsion or oil-bound distemper, or simply color wash if case this specification for finishing is not the plastic emulsion may be selected for the finishing in case very high-end specifications are selected for the building, while oil-bound distemper and or simply color wash may be selected for the finishing if case the specifications are not or medium to modest and the cost is to be within the budget. Plaster with oil-bound distemper is an example of a medium uh, mid-level specification for the finishing that is neither too costly nor too economical. Similarly, roofing material may be selected again depending on the location and the weather conditions. Example of roofing material that are that is that are commonly implemented for the roofing and waterproofing of the surface of the roof are mangalore tiles for with bitumen, for example, where bitumen is provided for waterproofing, or brick cover. So, considering the dead weight of the non-structural elements based on the flooring, finishing and the roofing material that are selected depending on the specifications for the finishing of the building, one can calculate all the dead loads that are required based on the self weights of the flooring, roofing and finishing materials. Continuing our discussion on the step-by-step methodology for the structural design process of a practical reinforced concrete frame building structure, such as the rail of a practical office building, for which the architectural floor plan of a typical floor is displayed in the figure of the assignment. The fourth step in the structural design process is to compute the lateral earthquake forces, also termed as design horizontal earthquake force or design horizontal seismic force or design horizontal seismic base shear in the terminology of the Indian Standard Code of Practice for earthquake resistant design of reinforced concrete building frames and building structures in general. The design horizontal seismic base shear, denoted as VB, is calculated for the idealized three-dimensional frame model, more popularly known as the space frame model of the practical building structure, such as the office building, for which the architectural floor plan of a typical floor is presented in the figure of the assignment. It is worthwhile to mention here that the steps 1, 2 and 3 presented in the previous slide on the step-by-step methodology for the structural design process of practical reinforced concrete frame building structures correspond to question numbers 1, 2 and 3 of assignment number 1, and therefore provide the details and guidelines for the methodology of performing the steps 1, 2, and 3 respectively of the structural design process for practical reinforced concrete frame building structures. In other words, steps 1, 2, 3, and 4 that are presented in the previous slide and the present slide provide the guidelines and the details of methodology for solution to question numbers 1, 2, 3, and 4 of assignment number 1, that is the steps 1, 2, 3, and 4 of the structural design methodology for practical framed reinforced concrete building structure. For example, the office building presented in assignment number 1. Therefore, in step number 4, we proceed to compute the design lateral earthquake force or the design horizontal seismic force calculated in the form of the design horizontal seismic base shear VB for the idealized three-dimensional frame model or the space frame model of the practical office building based on the structural framing system or structural framing plan developed in part 1 of the assignment. Now, in order to facilitate the computation of the design horizontal seismic force or the lateral earthquake force calculated in the form of the design horizontal seismic base shear VB computed in the two horizontal or principal orthogonal directions of the building VBX and VBY in the horizontal orthogonal or principal directions of the building X and Y respectively. A worksheet that summarizes the formulations and seismic parameters that need to be computed for the earthquake resistant design in order to calculate the design lateral and vertical earthquake forces deemed to be acting on the three-dimensional building frame model or the space frame model of the office building considered in assignment number 1. Therefore, as an exercise, the students are requested to refer to the worksheet that summarizes the earthquake resistant design methodology or the seismic design methodology for calculating the design lateral and vertical earthquake forces acting on the three-dimensional frame model of the office building based on the structural framing plan or structural framing scheme developed in part 1 of the assignment number 1. As you will note or observe from the worksheet that summarizes the formulations and parameters for seismic design methodology of practical reinforced concrete frame building structures, the seismic design formulations and parameters that are required for calculating the design horizontal and vertical earthquake forces on the idealized three-dimensional frame model or the space frame model are presented in the appropriate sequence that facilitates the computation of the design horizontal seismic force and the design vertical seismic force on the idealized three-dimensional frame model or the space frame model of the office building. Therefore, referring to the worksheet that is uploaded on the Impartus link of the Moodle website for the course for the earthquake resistant design of the practical reinforced concrete frame building structure in order to calculate the design horizontal and vertical seismic forces deemed to be acting on the idealized three-dimensional frame model or the space frame model of the practical or real office building. Well, once the design horizontal and vertical seismic forces or the earthquake loads calculated in the form of the design horizontal seismic base shears VBX and VBY are calculated in the two horizontal, orthogonal or principal directions x and y of the building, following the recommended sequence of calculations in the worksheet uploaded on the Impartus link of the Moodle website. The next step is to distribute, or rather, the next task in step number 4 is to distribute the design horizontal seismic forces or the design horizontal seismic base shear calculated in the two orthogonal or principal horizontal directions of the building, following the recommended sequence of calculations in the worksheet uploaded on the Impartus link of the Moodle website for the course. On the earthquake resistant or seismic design methodology for practical reinforced concrete frame building structures. Having calculated the design horizontal seismic base shear in the two horizontal orthogonal directions of the building, that is VBX and VBY, the design horizontal seismic base shears in the two horizontal orthogonal directions X and Y of the building respectively, we proceed to distribute the design horizontal seismic base shear thus computed using the worksheet for computation of the design horizontal earthquake forces among the various floors or levels of the three-dimensional building frame model or the idealized 3D or space frame model. The sequence of computations that are to be followed for distributing the design horizontal seismic forces calculated in accordance with the response spectrum method of the Indian Standard Code of Design Practice for Earthquake Resistant Design, IS 1893 2016, for building structures is illustrated in the worksheet or the summary of the seismic design methodology and seismic design parameters uploaded on the importance link of the Moodle website for the course. Therefore, calculating the horizontal seismic forces in the two orthogonal horizontal directions x and y, or the horizontal seismic base shears denoted as VBX and VBY in the horizontal orthogonal directions x and y respectively, following the systematic sequence of computations summarized in the worksheet for seismic design methodology and seismic design parameters uploaded on the importance link of the Moodle website for the course. The design horizontal seismic base shears thus computed and denoted as VBX and VBY in the two horizontal or principal orthogonal directions x and y respectively will be distributed to the various floors or levels of the idealized three-dimensional building frame model or the idealized space frame model of the building. To obtain the story forces acting on the idealized three-dimensional building frame model or the space frame model, the next task in completing step number 4 is then to distribute each of the story forces computed as explained above in either of the two and each of the two horizontal, orthogonal or principal directions x and y to the individual equivalent two-dimensional planar frames or the idealized plane frame models that are obtained by discretizing the idealized three-dimensional building frame model or the space frame model into series of equivalent two-dimensional planar frames or plane frame models spanning in the respective directions x or y. And the distribution of the design horizontal seismic story forces acting on the various floors or levels of the three-dimensional building frame model or the space frame model in any one of the two horizontal, orthogonal or principal directions x and y is performed using the formulations presented in the simplifying idealization number 3, presented in earlier lecture notes and illustrated in the earlier lectures for distributing the horizontal seismic earthquake story forces thus obtained using the systematic sequence provided in the worksheet. Among the individual equal and two-dimensional planar frames or idealized plane frame models discretized and spanning in the respective horizontal, orthogonal or principal directions x and y, thus resulting in the design earthquake loading or design earthquake loads on the individual idealized two-dimensional plane frames or the individual plane frame models for the purposes of structural analysis of the individual plane frame models in 2 dimensions. Well, the current slide, titled as the annexure, provides the details of the methodology for distributing the lateral earthquake forces or the horizontal seismic forces calculated in the form of design horizontal seismic force or design horizontal seismic base shear in accordance with the response spectrum method specified by the Indian Standard Code of Design Practice for Earthquake Resistant Design of Building Structures, IS 1893 2016, that are deemed to act on the three-dimensional frame model or the idealized 3D frame model, more popularly known as the space frame model of the practical reinforced concrete frame building structure, that is the real or practical office building, for which the architectural floor plan of a typical floor is shown in figure 1 of assignment number 1, and the distribution, as we discussed in the previous slide, of the lateral seismic forces or the design horizontal seismic force calculated in the form of the design horizontal seismic base shear in each of the two horizontal or principal orthogonal directions of the building is performed to determine the share of the design horizontal seismic force or design horizontal seismic base shear in the respective horizontal or orthogonal or principal direction x or y that is resisted by the individual idealized two-dimensional planar frames or idealized plane frame models obtained by discretizing the idealized three-dimensional frame model or the space frame model into a series of individual idealized plane frame models along each of the two horizontal orthogonal or principal directions x and y. For example, plane frame 1 1 as labeled on the structural framing plan that was conceived or developed for the office building considered in assignment number 1, for which the architectural floor plan of a typical floor is shown in the figure of assignment number 1. And the other plane frame models, for example, plane frame models 2 2 3 3, discretized along the y-axis and along the x-axis, the idealized 2D planar frames or plane frame models AA, BB, CC, DD, and so on, discretized along the x-axis, not shown in this figure. Therefore, based on the structural framing plan or the structural framing scheme that was conceived or developed on the basis of the architectural floor plan of a real or practical office building constructed as a reinforced concrete frame building structure, that is presented in the figure of assignment number 1 and also reproduced here in this figure on this slide. The present slide, which is serving as an annexure to the previous slides, details the methodology of the distribution of lateral earthquake forces or horizontal seismic forces calculated in the form of design horizontal seismic force or design horizontal seismic base shear in each of the two horizontal or principal orthogonal directions x and y to the individual floors of the idealized three-dimensional building frame model, more popularly known as the idealized space frame model, and further distributed to the individual idealized 2D planar frames or the plane frame models obtained as a result of discretization of the idealized 3D frame model or space frame model into series of equivalent two-dimensional planar frames or plane frame models in each of the directions in the horizontal plane. As a recap, let us revisit our structural framing plan or the structural framing scheme that we developed following the practical or empirical guidelines for generating structural framing plans or structural framing schemes of real reinforced concrete frame building structures. For example, the office building presented in assignment number 1, for which the architecture floor plan of a typical floor is displayed in the figure of assignment number 1. Therefore, revisiting the structural framing scheme or structural framing plan that was conceived or developed as solution to question number 1 of assignment 1, and based on the practical or empirical guidelines for development of structural framing plans, that are economical as well as structurally viable in as detailed in the first step of the step-by-step methodology for the structural design process of reinforced concrete frame building structures. Well, recall that the first empirical or practical guideline for optimizing economy versus structural strength is to locate the beams under each full height wall so that the beams support the full height walls as highlighted in this figure. The exterior walls, which are 230 mm thick, are full height walls, and therefore following the first empirical or practical guideline, the exterior walls should be supported by beams in order to ensure that the dead weight or the dead load of the filler walls or the brick masonry infill panels that are provided on the periphery of the building is transmitted directly to the beams and not on to the floor slabs, since the floor slabs will become uneconomical in case the brick masonry wall panels or filler walls rest directly on the floor slab. Well, in addition to the exterior walls that are 230 mm thick, as they are constructed as full brick walls with the cross section shown here in this section. There are interior brick masonry walls that act as partition walls and are 115 mm thick but are full height walls, and therefore following the empirical or practical guideline number 1 for optimizing economy versus structural strength, all the interior partition walls that are constructed as full height brick masonry filler walls or full height brick masonry infill walls should also be supported by beams, and therefore the beam layout can be completed following the empirical or practical guideline number 1 that we discussed in one of the earlier lectures, by providing beams under each of the full height brick masonry filler walls or brick masonry infill walls, regardless of whether these are exterior walls which are 230 mm thick or interior walls that are 115 mm thick, in order to ensure that the full height brick masonry walls do not rest directly on the floor slab, in which case the floor slab thickness will increase excessively, thus rendering the floor slabs to be uneconomical. So, as highlighted by this yellow line, the interior as well as the exterior brick masonry filler walls or brick masonry infill walls are provided with supporting beams or beams that support the pillar walls. Following the rationale of the empirical guideline or practical guideline number 1, the layout, the beam layout can be finalized as shown. Or represented by the yellow lines which depict the beam layout and that conforms to the first practical or empirical guideline for optimizing economy versus structural strength. There is one more beam, maybe. Well, another consideration that has been applied in arriving at this beam layout depicted by the yellow lines is that the beams and therefore the frames in each of the two horizontal orthogonal directions x and y should be as long as possible. For example, the beams and therefore the frames in the two horizontal orthogonal directions x and y should be as long as possible in order to mobilize the frame action to the maximum. As one can intuitively visualize, that longer the frames in any horizontal orthogonal direction, the longer will be the more efficient and effective will be the frame action. Therefore, continuing the beams and therefore the frames across all the way through from one end of the building to another end of the building is structurally beneficial and advantageous, since long frames offer more effective and efficient structural frame action or structural load resisting mechanism And following that structural consideration, we have located our beams such that all the full height brick masonry filler walls or brick masonry infill walls are supported by beams as well as long frames. The length of the beams are as long as possible the total length of the beams, and therefore the resulting frames are as large as possible, thus resulting in or providing more efficient frame action or structural load resisting mechanism due to the moment resisting frame action in each of the two horizontal orthogonal directions X and Y. Well, so based on the rationales for maximizing the structural frame action or achieving the most efficient and effective structural frame action, it makes structural sense to connect the beam or extend the beam supporting this full height wall all the way up to the lift or the elevator core wall, represented as the double thick line, and the cores represented as the crossed out hollow spaces that accommodate the elevators or the lifts. So, in order to achieve the most effective and efficient frame action, the beams have been extended to span into the elevator or lift core walls that are solid RC, reinforced concrete core walls, so that the frame action is most effective and efficient. And long frames across the length of the building along the horizontal orthogonal direction X are achieved, and similarly the beams in the Y direction that are located under the full height brick masonry walls or filler walls or infill walls are also extended throughout the width of the building in the Y direction to ensure that the longest possible frames are formed, that is, the plane frames in each of the two horizontal orthogonal directions X and Y have the longest possible length, highest possible length, thus providing the most effective and efficient frame action in the two horizontal orthogonal directions X and Y. Continuing our recap on step number 1 of the step-by-step methodology for the structural design process of reinforced concrete frame building structures, as solution to the question number 1 of assignment number 1, wherein we are required to develop or conceive an economical and structurally viable structural framing plan or structural framing scheme for the real or practical office building constructed as a reinforced concrete frame building structure, for which the architectural floor plan of a typical floor is provided in the figure of the assignment and reproduced here. The other practical or empirical guideline for optimizing economy versus structural strength is to locate the columns in the envisaged structural framing scheme such that the spacing between any two adjacent columns lies in the economical range of column spacing, which is 3 to 9 meters, the economical range of column spacing that has been observed from past experience or practice with similar building structures. Therefore, following the second empirical guideline for locating the columns such that the spacing between any two adjacent columns lies within the economical range of column spacing based on past experience or past practice, observed as 3 to 9 meters, will locate the columns at spacing of 3 meters, for example, since, as we mentioned earlier, the smaller the spacing between the columns, the larger or more effective the frame action, and lower the vertical gravity loads that are resisted by any individual columns, and more the number of columns in each of the two orthogonal or principal horizontal directions x and y, thus resulting in a smaller cross section or a more economical cross section for each column. So locating the columns based on the practical empirical guideline number 2 for columns, for economical column spacing, that should be in the range of 3 to 9 meters. Since none of these columns are interfering with the functional requirements or the function of the enclosures of the floor as depicted by the architectural floor plan. In other words, since none of these columns are interfering with the function or the intended use of the different enclosures depicted in this architectural floor plan, and the column spacing between any two adjacent columns is 3 meters, which is within the economical range of column spacing as per the practical or empirical guideline. And the aesthetic or architectural preference of concealing the columns within the brick masonry filler walls or the brick masonry infill wall panels as far as possible is also satisfied, to the extent possible, depending on the cross-sectional dimensions of the column. And the columns are allowing the maximum feasible usable space while not interfering with the function or the intended use of any enclosure. The proposed location of the columns as shown in the figure, well, which is not exactly to scale, or rather not to scale at all, should be acceptable from the point of view of optimizing economy versus structural strength, as well as accounting for the architectural, functional, and aesthetic requirements or preferences that we have discussed in quite some detail in the earlier slide on the first step, that is step number 1 in the step-by-step methodology for the structural design process of reinforced concrete frame building structures, as solution to question number 1. On the development of the structural framing plan or structural framing scheme for a practical or real reinforced concrete frame building structure such as the office building, for which the architectural floor plan of a typical floor is presented in figure of the assignment number 1 and reproduced here, along with the completed structural framing plan displaying the locations of the beams highlighted by the yellow marker and the location of the columns marked by red rectangles. It is worthwhile to mention here that since the columns are rectangular in cross section, as in case of practical frame building structures, the shorter dimension of the columns are aligned along the longer dimension of the building, while the longer dimension of the columns are aligned along the shorter dimension of the building, which is intuitively reasonable, since columns have different stiffness and strength along the major axis and minor axis. It makes sense to align the columns such that the shorter dimension or the minor axis of the columns are aligned along the longer or the stronger dimension of the building, that is, the stiffer dimension of the building, while the longer dimension of the columns, that is, the major axis of the column, the minor axis of the columns are aligned along the shorter or the weaker dimension of the building. Well, the structural framing plan, that is represented by the layout of the beams highlighted with the yellow marker, and the columns